In this lecture we are going to see the losses in transformer. Basically there are two losses in transformer, which are iron loss and copper loss. Let us see first iron loss. This loss is also known as core loss. So iron loss occurs in core due to flux reversal. As flux is changing because it is alternating, so due to this reversal of flux in core, this loss occurs, right? In transformer core, flux is almost constant always. Flux is always constant in transformer core. Therefore, this loss is also known as constant loss because flux is constant. So loss is also constant. Right. It does not depend on load. So the loss is remaining constant from no load to full load. No issue whether load is present or absent or it is partial. The flux is constant, therefore loss is also constant. And this loss is further classified as hysteresis loss, denoted by pH, and second is eddy current loss. Eddy current loss denoted by P. So let us see first hysteresis loss. This loss is due to alternating flux in the core. If I draw BH curve, this is field intensity H and this is flux density B. So at a particular field intensity, flux density, say this is B max, and here field applied is H max. Now if I reduce flux from H max towards 0, flux density also decreases, but flux density is not becoming 0 when field is 0. So this is because of the property of material, and this flux is what? Residual flux. So to bring this flux density to 0, I have to apply extra field in opposite direction. See here, field from 0 is applied up to this one in opposite direction, and at this point flux density is what? 0. And if I go on increasing applied field in opposite direction, the flux density will again build up and it will become maximum or will go in saturation at H max, that is minus, right, opposite direction. And again if I reduce flux magnetic field strength from minus H max towards 0, the flux density will decrease, but it will not go to 0 value when field is becoming 0. And to bring this flux density to 0, extra field in positive direction is applied. Now here the field is brought to this position, then flux density is what? At this x-axis flux density is 0. And if I further increase field in positive direction, then flux density will follow this path. So to bring field to bring flux density to 0, we have to apply this extra field, right? And here also to bring flux density from this value to 0, we have to apply this extra field. So this extra field is nothing but loss, which is known as what? Hysteresis loss. Hysteresis loss. And this loop is known as hysteresis loop, right? Area of this loop is going to decide the loss. This loss is given by pH equal to kh bm power eta f into v, where kh is constant of proportionality, bm is maximum flux density, f is frequency of flux reversal, and v is volume of core, not voltage. Eta is known as Steinmetz constant. Steinmetz constant, and its value is ranging from 1.5 to 2.5. For ferromagnetic material, eta value is approximately 1.6, right? So this hysteresis loss can be reduced by using soft and good magnetic material, which is what? CRGO, cold rolled grain oriented silicon steel. So this loss can be minimized by selecting good magnetic material. Coming to second iron loss, that is what? Eddy current loss. So eddy current loss occurs in core because of eddy EMF induced in core. We know that alternating flux is there inside core, so this alternating flux will induce EMF by Faraday law of electromagnetic induction, and this eddy EMF is circulating eddy current, right? And because of that eddy current, there is eddy current loss, and this loss is given by PE equal to KE BM square F square T square V, where K is constant, BM is again flux density, and F is frequency of flux reversal, V is volume, and T is what? Thickness of core. Thickness of core, right? And this loss can be minimized by doing lamination, also by reducing thickness of lamination, as we see from this eddy current formula. As T decreases, eddy current also decreases, and this loss can also be reduced by adding a small amount of silicon in steel. We know that silicon addition will increase resistivity of steel, because of that the eddy current will reduce, therefore eddy current loss will also reduce. So this is about iron loss. Coming to next loss, that is what? Copper loss. Second loss is copper loss. We know that the transformer primary and secondary windings are made of copper or aluminium, so these windings will have resistance, and if I say R1 is primary winding resistance, and R2 is secondary winding resistance, and if I1 and I2 are primary and secondary current, then copper loss will be given as PCU equal to I1 square R1 plus I2 square R2. As windings are having resistance and when current is flowing in winding, there will be copper loss, that there will be loss that is known as copper loss, I square R loss, right? We know that as the load changes, current will change. So in transformer, both primary and secondary current will change with change in load. Therefore, copper loss will also change. Therefore, this loss is also known as what? Variable loss. This loss is variable loss. So this is it for losses in transformer.